I'm tackling a problem about optimizing MiniBatchNMF, a scikit-learn tool for non-negative matrix factorization, NMF. The goal is to speed up calculations on huge datasets. Think of NMF as a way to break down a big data problem into smaller, more manageable parts. We'll examine the effects of different parameters to achieve this. We'll assess several statements to determine their accuracy in optimizing MiniBatchNMF for performance. We're looking for statements that are factually correct and relevant to enhancing performance. This refers to the specific algorithm, MiniBatchNMF, from the scikit-learn library, which is designed for efficient NMF on large datasets by processing data in batches. This is crucial for dealing with large datasets that may not fit entirely into your computer's memory. I'm looking at the _max_iter parameter, which sets the maximum number of iterations the algorithm runs. Increasing it usually improves the quality of the factorization, but it always comes with increased computational time. More iterations mean more processing. It's a trade-off between quality and speed. I'm considering _random_state . This parameter sets a seed for the random number generator. Changing it affects the starting point of the algorithm, possibly leading to different results, but it won't make it faster or slower. It's all about the randomness, not the speed. I'm evaluating the impact of the _batch_size parameter. A smaller _batch_size means more batches, and more batches generally translate to more total computation time even though individual iterations might be quicker. It's like taking many small steps versus a few large ones. More steps takes longer, even if each step is smaller. I'm analyzing the _n_components parameter, which determines the number of latent features the algorithm aims to extract. Increasing _n_components makes the problem more complex, leading to a significant increase in computation. It's like trying to solve a much harder puzzle with more pieces. It will take longer. I see max_iter as the maximum number of iterations the algorithm will run. Increasing this value allows the algorithm to potentially find a better solution, but it also means more computation time. Think of it like this. You want to find the best spot on a mountain. Increasing max_iter is like taking more steps. More steps means you're more likely to find a good spot, but it takes longer. The _batch_size parameter controls how much data the algorithm processes at once. A smaller batch size means more frequent updates, potentially speeding up the early stages of the process, but it might increase the total computation time because more iterations are needed to process all the data. It's like eating a big pizza. You could take one big bite and be done quick, or you could take small bites and savor the pizza, but that takes more time. The _random_state parameter sets a seed for the random number generator. Think of it as setting the starting point for your algorithm's journey. Changing it changes the starting point, potentially changing the resulting solution, but it won't affect how quickly your algorithm reaches its solution. It's not affecting the speed of the journey. I interpret _n_components as the number of underlying features we're trying to extract from the data. Increasing this number increases the complexity of the calculation, leading to increased computation time. It's like trying to describe a complex image using more and more simple shapes. The more shapes you use, the more precise the result could be, but also, the longer it takes to put it all together. The term, large dataset, emphasizes that we're dealing with a substantial amount of data, which makes computational efficiency particularly important. All parameter choices must be weighed against the trade-offs between computational cost and solution quality given that we are working with a large dataset. I'm examining how different parameters in scikit-learn's MiniBatchNMF affect its performance with large datasets. We'll look at how each parameter impacts speed and accuracy. This is a multiple-choice question testing your understanding of how MiniBatchNMF parameters behave. I'm focusing on 4 key parameters within MiniBatchNMF. _n_components _max_iter _batch_size and _random_state . Understanding these is crucial for optimizing performance. This parameter determines the number of latent features MiniBatchNMF will extract. A higher number means more features, but that also increases the computational cost. This sets the maximum number of iterations the algorithm runs. More iterations can lead to a better solution, but it also takes more time. This controls the size of the data chunks MiniBatchNMF processes at once. Smaller batches mean more iterations, impacting overall speed. It's a trade-off between iteration speed and the total number of iterations. This parameter controls the random number generator. It doesn't affect speed, but changing it might alter the results slightly because of the algorithm's randomness. This phrase simply introduces the core topic: how different parameters within the MiniBatchNMF algorithm affect its performance, specifically focusing on its efficiency when handling large datasets. It sets the stage for the analysis of the parameters and their impact on computational speed. This line presents the central question of the quiz: which statements accurately describe the effect of altering different parameters in the MiniBatchNMF algorithm? I'm looking to identify the true statements regarding how those parameters impact processing speed and quality of results on large datasets. This statement is about the parameter MAXITER, maximum number of iterations. I see that increasing MAXITER will improve the results because the algorithm will have more steps to refine the factorization. However, more iterations mean more computation, and hence, more processing time. This is a trade-off between accuracy and efficiency. This statement focuses on the BATCHSIZE parameter. I found that it's incorrect. While a smaller BATCHSIZE does make each iteration faster, it requires many more iterations to process the entire dataset. This significantly increases the overall computation time. It's a classic case of diminishing returns. This statement is about the RANDOMSTATE parameter, which controls the randomness in the algorithm's initialization. I see that changing it does not change the computational speed. But, because of the random nature of the algorithm, it will likely lead to slightly different results each time you run it. This simply labels the section on dataset considerations. The algorithm's performance depends heavily on the characteristics of the dataset, especially its size. This refers to the specific scikit-learn algorithm used, MiniBatch non-negative matrix factorization. It's a variation of NMF designed to be more efficient for large datasets by processing data in batches, making it well suited to the problem at hand. This title tells you what we'll be exploring: how different settings, parameters, in the MiniBatchNMF tool affect how quickly it works, especially when dealing with massive amounts of data. We'll focus on how each parameter influences speed and the quality of the results. It's like tuning a car engine. Each part has an effect on performance. This is the main question. We're using MiniBatchNMF from scikit-learn, a popular Python library for machine learning, to break down a big dataset into smaller, easier to manage pieces. We're trying to do this efficiently, so we'll look at how parameter choices can speed things up. Think of it like optimizing a recipe to minimize cooking time. This controls the number of times the algorithm attempts to improve its factorization result. More iterations can lead to better results, but it also slows things down, like taking extra practice laps before a race. It's a trade-off: higher quality versus longer processing time. This sets how many data points the algorithm processes at a time. Smaller batches mean more iterations to cover the entire dataset. While each iteration is quicker, the total time goes up, kind of like taking many small steps instead of fewer bigger ones. Larger batches might be faster overall. This sets a seed for the algorithm's randomness, controlling its starting point. Changing this doesn't speed things up or slow things down. It only affects the specific result you get due to the algorithm's random choices. Just like setting a specific starting point in a maze doesn't change how long it takes to solve it. This determines the number of features the algorithm extracts. More features mean more complex calculations, making the whole process slower. Think of it as trying to describe something using many tiny details. It is more precise, but takes longer. This quiz focuses on how different parameters in scikit-learn's MiniBatchNMF, MiniBatch non-negative matrix factorization, affect its performance, especially when dealing with large datasets. We'll look at how changing each parameter affects speed and accuracy. This question asks us to identify which statements accurately describe how changing MiniBatchNMF parameters impacts performance. We need to think critically about the effect of each parameter change. I agree with this. Increasing MAXITER, maximum number of iterations, allows the algorithm to run for longer, refining the factorization. This usually improves accuracy, but it takes longer. It's a trade-off between accuracy and speed. I think this is true as well. The RANDOMSTATE parameter sets a seed for the random number generator. Changing it doesn't change how fast the algorithm runs, but it can lead to slightly different results each time because the algorithm starts at a different random point. I disagree. Increasing NCOMPONENTS, number of features to extract, makes the problem more complex, leading to slower processing. Think of it like this. You're trying to find more pieces of a puzzle. It's going to take more work. I'd say that's false. Reducing BATCHSIZE, the amount of data processed in each step, might make each iteration faster, but you'll need many more iterations to process the whole dataset. The overall time often increases because of the higher number of iterations needed. I'm asking you to identify which statements correctly describe how to use the parameters of the MiniBatchNMF algorithm, a type of non-negative matrix factorization, to speed up its performance when dealing with large amounts of data. Remember that MiniBatchNMF works by processing data in smaller chunks, making it suitable for large datasets. We'll consider the effects of changing each parameter. Increasing MAXITER, which represents the maximum number of iterations the algorithm runs, can lead to a better factorization. But more iterations mean more calculations, and that directly translates to longer processing time. It's a trade-off between better results and computation speed. The RANDOMSTATE parameter sets the starting point for the algorithm's random number generator. Think of it like choosing a different starting point for a race. It doesn't change how fast someone runs, but it might change the final outcome. Changing this won't make the algorithm faster or slower, but it could lead to slightly different results. This statement is incorrect. Increasing NCOMPONENTS, the number of features you're trying to extract, actually makes the computation much harder. More features mean more calculations, leading to slower processing. This is also false. BATCHSIZE refers to how much data is processed in each step. A smaller BATCHSIZE means more steps are needed to process all the data. Even though each step is faster, the overall time increases because you need more steps. It's like taking many small steps instead of a few large ones. You might arrive faster with larger steps. MiniBatchNMF is a specific algorithm in Sklearn, a popular Python library for machine learning, designed for non-negative matrix factorization, NMF. It's optimized for efficiency on large datasets because it processes the data in smaller, manageable batches, hence the name, MiniBatch. This refers to the number of features the algorithm attempts to extract from the data during NMF. It represents the dimensionality reduction of your data. This parameter sets a limit on the number of cycles, or iterations, the algorithm performs. Each iteration is a step towards finding the best representation of the data. This dictates how much data the algorithm works with at once during each iteration. This is a seed value used to initialize the random number generator. It affects the randomness in the algorithm. The same random state will give you the same results. This is referring to datasets too large to comfortably be processed in memory all at once, commonly encountered in machine learning scenarios. This is the result of applying the non-negative matrix factorization algorithm to your input data.